Hi, welcome back. So now we should be familiar with the command pipeline center and how to basically build pipelines, and we're comfortable with Visual 3D in general. So going onward, we're just gonna focus on certain specific biomechanical analyses. Today we'll focus specifically on inverse kinematics and inverse dynamics. So how to build and how to calculate joint angles and angular velocities, and their derivatives, whatever you want, to do with after that. So once you have the joint angles, you can do and calculate like joint angular velocities and angular accelerations. And also we'll work on inverse dynamics, so how to build joint moments. All right, so we'll keep working on our workspace, just the same data. And in here I created this pipeline, and I will provide all the pipelines for all these tutorials so you can follow, but I recommend you to do it yourself so you can understand, and only use the pipelines if you're having troubles creating some specific outcome measure. Then you can go back to the pipeline, but I always recommend to first do it yourself so you get familiar with the process, and then also remember the exact process, so you don't really rely on anyone else. All right, so again, we'll first start with the save as, just in case you mess up later on, you always have a backup to go back to your original data before you started like processing, and then reprocess your data, whatever, like however you want to do it. All right, then save and then select active files. We're working with this specific tag of 3 motion trials of this older participant, so you choose all of them. All right, so the first thing, let's start with joint angles. Okay, so when you go to see motion and you type joint angles, it will give you like a lot of options. um, let's write joint angles, but make sure you go to the tutorial model-based computations, because the command here is model-based computations. Model-based computations will give you the option to run a lot of biomechanical outcome measures. So here, when you choose any of these, it will give you like all of these options. So here you just choose the name, and here the outcome folder, you can choose that. You can change that in the text in here if you really want to change the folder, but you can just keep it original. The original folder is fine. It doesn't make a big difference. So here actually you don't actually see it. It's by default. They make people choose the original, but you can actually code it in, like you can hard code it. So in here, result name, you just need to like type result folder, like. And then you can just type any folder you want, like processed, whatever. But that's if you want to do that, but it's more user friendly this way if you would like that, to make your life easier. But here, model based item properties, you can either choose from all this long list, joint acceleration, joint angles, joint rotations, joint force, joint moments, powers, anything really you want. It gives you a lot of options on what your outcome measure you want it to be. So here, first we focus on the joint angles. So a tutorial here is again, you type joint angles and then you go to model-based computations, and tells you exactly um, what to do. So the first thing here you need to note is the orientation. You have to make sure that the orientation is correct. So x is ML, y is AP, and z is vertical. If it's not, then make sure your outcome measure is based on the orientation of your lab. Okay. All right. So to build the joint angles, we'll first start with the distal and then work our way up. So we'll first start with the right ankle angle. So you just name it whatever you want in here, and then choose the folder, and then click on joint angle in this section. And then in terms of the segments, you always choose the distal segment first, and then the reference segment will be the proximal. So in case of the ankle, we choose the segment as a distal segment, which is the right foot, in case of choosing the right ankle angle. And the reference segment will be the proximal one, so that's the shank, the one that is closer to the center of mass. So we chose those, and then the the coordinate sequence has to be the same as your coordinate system. So x, y, z, just make sure you know it's the same as your coordinate system, and then hit done. And then let's, like, for example, step this. I already have it, but it's just gonna override it. So when you go here to link based model, or link model based original, you'll find your outcome measure in here. So we just ran right ankle angle, and then see it here. So if you focus on the right ankle, obviously we use the right hand rule. So I'm gonna tell you that here. So if you're looking for sagittal plane, the sagittal plane rotates around the x-axis, as you can see there. So we have the x-axis in here. The axis is pointing this way, and it's rotating along the x-axis to produce the flexion extension. If you'd like the abduction and adduction, then you search for the y-axis, and the z-axis will be transverse, so internal external rotation. So here, when you look at the x-axis, you can see that the right ankle here is plantar flexing, and then on the swing phase it will be, so it's plantar flexing, then in the swing phase will be dorsiflexing in here. But when it goes on positive, you can clearly see that they're actually hyper dorsiflexing their ankle to make sure they don't trip in this case. So positive is dorsiflexing, negative is plantarflexing in the x-axis. Alright, so we got that covered. Let's move on to the knee. The knee is a little bit different because the flexion and extension is actually opposite to other joints. So because the knee angle, the knee right here, it's when it's flexing, it's actually flexing opposite to, for example, the ankle or the hip or the trunk, or pretty much all other segments, because when you flex towards the center of mass. Here flexion is opposite, but it's basically it's closing between the shank and the thigh, but it's not closing inside the center of mass, if that makes sense. For example, if you look at the hip, this is like the right hip right here. When it's flexing, it's closing towards the center of mass, towards the trunk. But when the knee is flexing, like right now, it's flexion and then extension. So flexion, extension, flexion. When it's flexing, it flexes towards the thigh, not really towards the center of mass. So when you build the right ankle angle, the right knee angle here, so you choose right joint angle. So the same process. You choose the right shank as a segment, so the distal, and then the reference segment as the proximal, so the thigh. You choose the same Cardian sequence, so XYZ, but you use the negative to get the right ankle, the right knee angle. If you don't use the negative, you'll see. It's just up to you, really. But when you, for example, use the negative, which is what I use to make my life easier, you see here, um, when they're flexed, their knees, we have a higher angle because it makes sense. Um, the closer they get to full extension, the closer to zero it is. So when they're full extension here, it's almost zero. It's like at 8.7 degrees, or 9.9 degrees, almost 10 degrees. So it makes sense, but the more it is flexed, the higher the angle is. But if you would like to have it negative, so if for example you run this whole thing um, without using the negatives, you will get the opposite basically. So the more it is flexed, the more negative it is. So like, see here, it's minus 74 degrees, but the more extended, the more it's closer to zero, so it's really up to you. I prefer to use positive values. That's what I'm used to. All right, and you keep doing the same thing for the other joints. So like for the left knee, the right knee, and then the hip is the same thing. So you always use the proximal for the segment, and the 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 distal for the segment, and then the proximal for the reference segment. All right, so let's go and do the angular velocities. So we did like here the right and left ankle angles, and then we want to explore the joint velocities. So you do the same thing, but instead of using joint angle, you use joint velocity in here, and then it's gonna ask you for the segment. It's the same thing, segment will be the distal right foot, the reference segment will be the proximal, so the right shank, and then also will ask you for the resolution of coordinate system, and you use the same thing as the reference segment. When we do the knee, same thing, so yeah, just follow that method. And like I said, if you want to learn more about the joint angles and the coordinate systems and so on, you can always go back to this page. I can provide this on the material for this specific tutorial. Alright, so the next thing is to run inverse dynamics. So with inverse dynamics, I'll first show you how to run the inverse dynamics as well, and then I'll also show you how to extract specific specific like outcome measures. For example, if you want to run the peak joint angle for the knee, so the peak knee angular velocity, or the peak knee joint, or the peak knee angle, between right heel strike and the next right heel strike, so within that stride. um, I'll show you how to do that, and also if you want to get the local, and that's basically called the global maxima. So the maximum joint angle across the whole trial, and then you use the global maxima. Or if you want like to get the local maxima, so all the peaks within each stride, you can use the local maxima for that. So let me first show you how to extract the joint moment, so like inverse dynamics. So to get the inverse dynamics, you can just also here they call them joint moments. I prefer joint torques, but it's the same. It depends on what you prefer. But when you type joint moments within the model-based item, it's the same. Same command. It'll bring you to this page. So we basically go with the same process. You name like the outcome measure here, and then instead of joint angle or joint angle velocity, use joint moment. And here you have two ways to extract the joint moments or joint torques to calculate inverse dynamics. So first of all, Visual 3D does the calculations for you, but you can choose two options. You either choose um, here the user can select the coordinate system in which to resolve this internal moment, but typically users choose either the proximal segment, so true of most segments, or the segment itself, often used for the knee moment. There is no right answer, but the user should report the resolution coordinate systems in any article to be published. First of all, you have to always, report everything in your publication. Be as detailed as possible. So for example, the following image contains a definition of the right knee moment where the moment is resolved into the proximal coordinate system. So here they basically shows the joint segment as a right knee, and then they use the proximal um, segment, which is the right thigh, as a resolution. You can also use the right knee, but use the Caden sequence, so basically resolving the joint moment using the joint coordinate system itself. In most cases, user will select to represent the joint moments as a vector. You can also like calculate the joint moments as a cross vector between the force vector um, and the segment vector of the knee, or between um, the joint angle and the force vector. But there has been a claim in the literature that it is more useful to represent the joint moment in the joint coordinate system, non-orthogonal coordinate system. So if you ask me, there's no really big difference between both, but always double check your data. Make sure that your data is correct. You can go back to this Gait and Posture publication in 2008 that specifically talks about this. But if you want to use this method, use like the right knee as a joint segment, and then you just click on use Caden sequence. And again, we're using the right thumb rule. Alright, so let's go ahead and do that. So I haven't really written it here, so we can do it together. Let's go to model based compute model based data, and here into the traditional way. So let's do right knee moment folder. Like even if you keep it empty, it will automatically do that for you. And then we choose joint moment, and here we normalize the data using default normalization, and then here we'll use the right knee, and then we'll first use the proximal, so the right thigh. Alright, and I click OK. I'm gonna make sure I've already created that in here. I created that using another. Alright, so let's step it. Everything's working fine, but then once you, I mean, it's the same thing, but we're just gonna show you like how it is. So here you see that the X is the sagittal plane for the right knee moment. So it's noisy obviously because we didn't filter anything, it just uses the original data, but you can filter this later on. You can filter this outcome measure to make it less noisy. But you can see here, positive is flexion and negative is extension. You see here they extended the knee, and you can see more clearly, you know. So this is the first method. The second method is you can always like do this. I think I mentioned it in one of the videos. So you can paste it here, and I'm gonna give you a new new command. So I change that name. So here, instead of like using the first method, second method is to use coordinate sequence. So it basically uses the same coordinates as the knee. So when we go here, let me just rename this. Alright, and then we step it. So here I'm gonna show you, for example, like the difference between both, and you can use this as well. So this is the one that we just made. This is the first method. You can see like the x, the sagittal plane is the same. Just a little bit of difference between the frontal and the transverse planes, but not too much difference. Just a little bit um, more wider. Um, the first one is less noisy as well. So it's not really like much difference. Just depends on you really. Also, you can right click here and then graph any axis you want. Let's remove all graphs, for example. Let's graph the first and let's graph the second, so you can see them side by side for the like you see them together, and compare the first and second methods. Compare the sagittal plane specifically here. So you can see like in terms of the sagittal plane, it's the exact same data. So it's up to you, and they do the same thing for all other joints. Alright, so once you create your outcome measures, here I've done this for like angular velocity of the left and right, size of the ankle, knee and hip. I also did the shoulders and the trunk and the elbows. So I have plenty of data in here. So when you finish building your or like calculating your outcome measures, all of your inverse kinematics and inverse dynamics, you can do you can extract like the global and local maxima using two options. You can either create events like we've discussed in the previous video, or you can just automatically like create the actual metric. So for events, you can just go like type event in here, and in the event creation, you'll see event global minima or global maxima, or event maximum, event minimum. So here in the event global maximum, you'll say place an event label at the global maximum value of a signal. So you just get in like the complete maximum. So the code will only look for the highest peak throughout the whole data and just picks that. The global minima, it will look for the lowest peak and it will pick that from the whole data. The event maximum, place an event label at the specified local maxima of a signal. So for example, if you specify um, if you just don't specify anything, and for example you want to run it on this joint moment that we just created here, so what it will do is I will pick all these maximums. So I will have one here, and one here, and even one here. So all the peaks, it will pick all the peaks. For the event minimum, it will pick all the minimums. But you can also specify here. For example, let's go here. So I created this first event global maximum as the peak right ankle dorsiflexion. So when you double click on it, it will be, again, like I mentioned, it'll be more user friendly if you want to go to the text, be more coding. So let's start with the basics. So here you choose like the event name. So I chose peak right ankle dorsiflexion. Select frame offset. If you remember, that's like the offset, so 0 for both time and frame. And then we choose the signal component as X because we know as the sensor plane rotates around the X axis. So I pick that, but here I wanted to extract the global maxima only when they were slipping. So that's why I chose the event sequence of slip start and slip stop. So I created these events prior to calculating anything. Obviously, when you have specific calculations you wanna run, first of all run your events like what we did. So we completed like um, the gate event, so the heel strikes and toes off, but also in that specific code I usually like extend that and add all the events that I need. So like the here slip start and slip stop, but also like if I have any other like events that I need to extract, for example like the peak velocity when the feet are like moving at their maximum speed, stuff like that. Depends on what you want to run. And that's it. So it's pretty straightforward. You can either do it like by hand or here like or more or by mouse. I prefer to like go here and just choose it. So it will, once you create this, like once you step it, you'll see it here in the event. For example, like if I step it, um, I did not create it because probably I don't have the right ankle angle. Do I have that? I think I have that. Right ankle angle. Because I don't have these two events. But for example, if I go here and remove this, it should give us that. So basically it will give us like, you see it was created. Let me highlight it so it's gonna be in green. So you see it here, the global maxima of the right ankle is gonna be right there. So you see, so when I click here, it's gonna say right ankle angle at frame 206, and here like it's that same thing. This is another, but it does basically it does pick like the global maxima for the whole thing. So you can either do that method or you can go and just create the global metric and just basically calculate that and just extract the metric itself. The reason why I did this is because if you have the event, you can choose that event in any other calculations, you know. But if you don't have the event, if you go, for example, and use the metric, so first of all, when you choose this, you just basically have to, if you want to extract the exact value of that global maxima of the ankle dorsiflexion, you go to metric signal value at event here. So when you type metric and filter, it will take you to metric. We have all these metrics. So you choose metric signal value at event. It will give you the exact value of that signal at the specific event that you created. So here, for example, I chose link based model, original right knee angle here, and then we'll ask you for the result metric folder processed within metrics, and then result metric name. You choose that name, and then you choose the sequence. So because it is flexion extension, it's the sagittal plane, you choose X, and then event name. So here it will ask you for that specific event that we just created. So you put that, and do the same thing for for all other like outcome measures. Or you can go here and just type metric maximum. And here it generates a maximum value of a signal as a metric. So the thing here is that it will just give you the local maximum, I believe. So if you use like metric maximum, it's gonna ask you for the resulting metric name, and then the folder of that metric, and then it's gonna ask you for the sequence. So if you want the global maxima, it's better to do the event. But if you just want to get local maxima, you can immediately just use the metric maximum, and it will give you the maximum value, all the maximum values here. Oh, but it can also, like, you can check this, compute maximum of the maximums. So it will basically give you local maximums, but also it will give you the global maximum, which is the maximum of those all local maximums. You have both options. I usually like use both. If I just want, like, if I'm sure that I only need that maximum, I just go ahead and use metric maximum to get the save me a little bit of time. But I prefer to use the event maximum, so I have that specific event, and then I can extract anything from those events. All right, so you do that, you get the global maximum of all that. But for example, here I have it from slip start to slip stop. You can get the global maximum from between those strides, between only those strides, between any sequence you want. But if you want to get the local maximum, for example, just go back to event creation, and then here, instead of like using global maximum or global minimum, we go to event maximum. So let's add that here. So we have the event maximum here. So peak right reflection, dorsal reflection, whatever. So what I'm gonna do is, like, I'm gonna copy the same name. So it's basically the same. See, it's the same outlook, you know, but one is event global maximum and one is event maximum, and you see it here on the top. So I'm just gonna go here and then here, but I'm gonna do like peak right ankle dorsiflexions local, and for the signal type, it doesn't like that. It wants me to do that, but it's fine. I just do it like here, so it's gonna be easy for you. Local, select frame window. Just keep it at 8, but you can change it to like any frames you want. Offset is 0. Single component, we just want the X. And then here the sequence, event sequence, for example, here, we want like from right heel to right heel, and that will give us the strides. And then you hit OK, and but it still wants us to do that, so I'm just gonna copy paste it from here. But either ways, you'll have to do it manually to write um, the actual signal that you want. So here, signal type, link based model. You keep it original because it is an original, and then come here. We need to get the actual name. That's why I mentioned this. Always good to have whatever outcome measure you need in front of you. So here, so we know it's on link model based. So we wrote that. It's an original, and then we type the signal name. So the signal name here is right angle. So we write like right. It's all capital. So it is capital sensitive. So you have to make sure that it is okay. Right angle X. All right, we're good. So when I step this, see, it gave us like all the events in here. So because it is local maximum, like I mentioned, so you see here it's like we have the global maximum, so the first one, and then the second one is the local maximum. So you see like here in the on the purple, it gives us all the um, local maxima between each of the right heel strikes. So here you see the right heel strike is in blue, so you see like between the right heel strike, so this is right heel strike here, it actually picked it around here, so between this and it actually picked the second one here. You see like it picked these. Obviously, you know, when they're slipping it's different than normal gate, but you get the idea. Alright, so again, you know, like I said, once you extract either the global, the local, whatever like event you need, then you just click on metric signal event, then you choose the signal type, link based model, we choose the folder is original, then the name is right angle, and then you choose the like the outcome measure to be saved where, you know, exactly. So here like I was gonna ask you about the metric signal folder, because the metric type here has processed, you know, or temporal distance. I will talk about that in a little bit in the next video, but basically you can choose, you know, the folder, like you can create a new folder, whatever you want, and then you choose the name, you choose the component, so X, and then the event, and it will save it here as what did we choose here? Peak right ankle dorsiflexion. So we go to peak. Okay, it's not there, so let me just run it. So once you run it, you'll see it here. So when we go to metric, go to P, you see like peak right ankle dorsiflexion, and also like we generate the mean for you if you have like multiple ones, you know, and you can choose that here. So when you run this, you can generate global mean and standard deviation as well. Alright, so that's about it for today's tutorial. I hope this helps, and see you in the next tutorial. Thank you.